This picture begins with a representation of the phenylalanine hydroxylase 117BH4 phenylalanine ternary complex, which includes an iron atom bound to 2 histidine residues and 1 monodentate glutamine residue. This complex has just enough room for 2 molecules of oxygen to bind inside and undergo a series of rearrangements before the phenylalanine substrate is hydrolyzed. This next picture depicts the same mechanism, but shows the transfer of electrons, as well as a more 3D representation of the active site, substrate, and cofactor. Here you can see that the iron molecule is an important aspect of the active site because it binds to the oxygen in some of the intermediates. The residues histidine 285, histidine 290, and glutamine 330 are also vital in this mechanism because they are responsible for stabilizing the iron molecule while it binds.
Man, that sure is complicated. So if phenylalanine hydroxylase is constantly working, how does it not use up all of our phenylalanine?
Great question, Harry. As I've mentioned before, phenylalanine is necessary for the synthesis of proteins and amino acids, but it can also lead to neurological damage if too much is present. As a result, phenylalanine hydroxylase must be strictly controlled to achieve an optimum concentration of phenylalanine. This regulation is achieved by 3 main processes: BH4 cofactor inhibition, substrate activation, and phosphorylation. In BH4 cofactor inhibition, the BH4 cofactor binds to the active site to form phenylalanine BH4 complex, which causes the enzyme to undergo a conformational change and pulls the N-terminus further into the active site. This change blocks off the active site to inhibit the substrate activation and enzyme phosphorylation. In addition to this, substrate activation can be used to regulate phenylalanine hydroxylase. Each molecule of phenylalanine hydroxylase has 2 sites at which phenylalanine can bind reversibly. Phenylalanine binding to the active site is what causes the molecule to be hydrolyzed into tyrosine. However, it is the binding of phenylalanine to the allosteric site that activates the phenylalanine hydroxylase. Once the allosteric site has a molecule of phenylalanine bound to it, the enzyme undergoes both local and global conformational changes, which moves the N-terminus and exposes the active site. Therefore, a molecule of phenylalanine must first bind to the allosteric site of the enzyme before the enzyme can hydrolyze a molecule of phenylalanine in the active site. In phosphorylation, a molecule of phenylalanine binds to the allosteric site of phenylalanine hydroxylase, and the conformational change allows the active site to be phosphorylated. This phosphorylation, which occurs at serine 16, causes a conformational change in the active site and displaces the N-terminus. As a result of these changes, there is an increase in not only the active site's accessibility, but also its affinity to phenylalanine.
Alright, so now we know how phenylalanine hydroxylase functions and how it's regulated, but how efficient is it?
Luckily for us, phenylalanine hydroxylase works pretty quickly. We can compare speeds of reactions by using dissociation constants. The smaller the dissociation constant, the faster a complex is formed. The binding of BH4 has a dissociation constant of 65 micromolar and occurs very rapidly. The binding of phenylalanine, on the other hand, is slower because it has a dissociation constant of 130 micromolar.
Are there any enzymes that are similar to phenylalanine hydroxylase?
There are 2 actually. Once phenylalanine hydroxylase synthesizes tyrosine, the amino acid is used to synthesize multiple neurotransmitters. During this process, tyrosine hydroxylase acts on the molecule and adds an additional OH group. Not only do these 2 enzymes have similar biochemical roles, but they also have similar structures. Both phenylalanine hydroxylase and tyrosine hydroxylase function as tetramers and utilize an iron ion. These 2 enzymes, along with tryptophan hydroxylase, which shares the functional and structural similarities, are called the aromatic acid hydroxylases because phenylalanine, tyrosine, and tryptophan all have aromatic rings in their structures. Because of these similarities, it is inferred that these enzymes have evolved from a common ancestor.
Man.
Created using Powtoon.